Hello and welcome back. Today we're going to solve a few more Rosetta code problems. So here again I have the list of tasks that are not implemented in Mathematica. So here we have this first list, which are fully defined tasks that have not been implemented yet in Mathematica. But there are also draft tasks, so those are not yet, let's say, finalized tasks without implementation in Mathematica. And well, from those I selected a few, as you see here in my tabs, and let's try to solve them. Alright, the first that I found that looked interesting were so-called Erdős primes. So Erdős primes are prime numbers such that all p minus k factorial for k prime between 1 and p are composite. So is that all prime numbers? So they should be not prime. Okay, write a program to determine and show all Erdős primes less than 2500. Optionally show the number of Erdős primes. Okay, stretch goal, show that the 7875th Erdős prime is that number. The highest below 1 million. Alright, as you can see I slightly modified my Rosetta task not implemented notebook with a new button, open new notebook. Alright, so well, let's save this notebook first. And let's try to solve this. So let's call this Erdős prime q n. So, well, the first requirement to it is that n itself is prime. If that is not the case, then well, we can immediately stop looking. But if it is prime, then we want to look for all k factorial such that, okay, yes. So let's start with k equals 1, I guess. Okay. While k prime is smaller than p, so the input should be p actually. That makes a little bit more sense. So while that is true, well, here of course we need to increment k. If p minus k prime k factorial, if this is prime q, then we want to return false, and if it survives this while loop, the thing is, what does this return? Does it exit the, well, we can test out. So let's say select from some range Erdős prime. So only 2. Okay, let's do a little bit bigger range. 101. 2500, right? So this seems to work already. So let's call this cell. Then we can also show the numbers 25. So that is basically the first task, and then we have to show the number of Erdős prime below 1 million. Well, that's also not so hard. Well, it's below 1 million, so let's do. Of course, I can simplify this a bit because many of them are not prime, but well. And then, well, also, so we want to show the last of them, and we want to show the length of that list. Maybe the other way around. So this will take a few seconds, I guess. Yeah, there it is. So that wasn't too bad. Am I logged in? Yes, I'm logged in. So let's change, let's add this. Let's copy this header again. go. And so we can copy the solution here. Copy. Looks all pretty good. And we can copy the outputs. Can I just do copy? Here we go. Let's remove the empty lines. Let's put that all on one line. Here we go. Save page. Let's have a look. That looks all good. Right, we solved the first one. Show on this page the first 9 prime Fibonacci numbers. Okay. Well, let's have a look. Fibonacci. Let's say 100. Let's get the first 100, and then select the first 9. Okay, is that the answer? Okay, it was pretty easy, but I would like to have a code without this explicit 100 here. So what we'll do is have a list which is empty, and then we'll make a do loop where I goes from 1 to infinity. So it's an infinite loop, actually. So if prime q Fibonacci I, then append to list comma this Fibonacci number. Let's call this f to save a little bit of computation. And then if the length of list equal to 9, then break. So, well, of course I can do both implementations. So this one, the second one, does not have the explicit, let's say some weird upper bound, let's say, that I'm looking for, which I don't know before. I might have needed 1,000 or 10,000. I didn't know. So what do people show here? Well, here's in Spanish. It's like same as the free basic entry. So it shows 9 of them. Same answer, same answer. So here people show 12 of them. Here people show 26 of them. So we can also go, we can try a bit higher. Let's say we want a first 15. That is pretty speedy. 18, also very speedy. 20. This is actually pretty fast code. So, so the Fibonacci numbers go very, very, very quickly, as you can imagine. So do we want to find the first 26 like they did in, what language is this? C++. So this took 20 seconds there. So I don't know how fast Mathematica will be. But it should be pretty fast. The prime, so people look for the first 23. So some people really stick to the required 9, but some people show off their language and show more than 9. So here we found the first 26. So let's actually submit both codes. We can do multiple entries. So what we can do is let's say first solution, and then not this one here. Calculation by guessing some upper bound, and then the output will be this. we can also do second solution without guessing some upper bound. I made a typo here. Here we go. And now I can also paste the second code. But I guess it's not so practical to show all the digits. So we have list now. So let's say if integer length list smaller than 10, then just show the thing. Otherwise, do integer digits of this thing and take the first, I don't know, 5. And take the last 5. So this is an array. This is an array. So let's join that all together. And now we say row of this. And let's maybe we want to add here how many digits they are. Tuk, 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 tuk. So I did something wrong. Yeah, I should put this in a little list here. Okay, let me see what people did. I think with this C code, yeah, so people also do digits. Maybe I can also, let's call this out. And then I say table form out, comma, table headings, automatic. Oh, I don't know the index. Okay, so what I can do is also store the index. Do first 15 just to see if my code works. There is something wrong here. Here we go. I do this. So this will make it turn into a row just to format it nicely. Do we want to add anything more? I think this is fine. Well, this if statement, what I can do is put it in here. Here we go. Let's add some dots here, some spaces around the dots. Here we go. Let's now calculate this 26 digits. And while I do that, let me update this code. Now it has changed. I must admit it's not the most beautifully written code ever, but it works. So let's run this for a second, it will take a while. Okay, here it's done. Let's copy this as some plain text. So of course the line here is not copied, but that is completely fine. And unfortunately the ellipsis, how do I type this thing again? Was it control? Okay, let me see what the ellipses look like. Is it this one? Okay. So unfortunately Mathematica doesn't copy the ellipses as character, so I'll manually replace it because that's what it would look like if you do it in Mathematica or Mathematica Online or the Wolfram language from the terminal basically. It's a bit of manual work, but that is fine. So let's have a look how this will look like before submitting. That looks all great. Let's say save. We also save this one, Rosetta prime Fibonacci. Here we go. Very nice. Done. Alright, last list item. Given this list, find the two smallest items, remove them from the list, find their sum, and add the sum to the end of the list. Repeat until the list contains one element. Show the steps and last item on this page. Show the unsorted list in output in case without sort. Show the unsorted list in output in case without sort. I'm not sure what that exactly means. All right, let's make a new notebook. Let's save this already. Last list item. So let's copy this exact list. So let's call it list. Here we go. Now we do some loop. And this will be done length of list -1 or 2. Let's see what it does. And what we do here is find the smallest two numbers, the position of the smallest two numbers. So I think we can use ordering for that. Give the position of the last n elements. So that is perfect. So this will be the positions. So let's do a print of that just to see what it will give. 7,3. No, I should do the smallest two. Here we go. Element 1 and element 2, 3, 4, 5, 6, 7, 8, 9. Good. So let's extract those. Extract from list. So do I have to put have to do this. Yeah, so let's call this extract. And then, well, we can take the sum of that. So find the smallest, remove the items from the list. So how do I remove? I can do delete list, and then delete the part, yes. So here we do again, do the list / add position. And then find the sum and add the sum to the end of the list. So what we can do, print list, oh, small list. Was that what I wanted? Let's do it one more time, I see. 621, that's very good. And now, so I guess this is without sorting. Well, with sorting, it is much easier. So let's first sort the list. All right, so what we do now, we take the first two, which are the smallest two always, or not? I'm not sure what the... So I don't see what the difference is between these two outputs. But I think one function assumes the list is sorted and the other one does not. So actually mine is then but also the with and without sorting. So I think this is it actually. So I don't know what I have to... Yeah, I think this is fine basically. The question is, do I also want to do a print of list here just to start off the process? So you see that 6 and 11 are added to 17 and so on. And then 14 and 17 are 31, etc. So let's do this one. So let's again copy my header here. Oh. And then let's also add this one with and without sorting. Maybe you can better do this, so it is a little bit of indentation. And then here we can copy this as plain text and remove the empty line. I think that is it. That is pretty easy. I'm not sure. So this is the problem, because this is probably a task that is like a draft here. It's a draft task, so it's probably not well defined what the difference is. But well, if people think it's wrong, they will tell me, I guess. All right. Euclid-Mullin sequence is an infinite sequence of distinct primes in which each element is the least prime factor of 1 plus the product of all earlier elements. The first element is usually assumed to be 2. So the second element is 3 and the third element is 7, as this is prime. Although intermingled with smaller elements, the sequence can produce very large elements quite quickly, and only the first 51 have been computed at the time of writing. Compute the show here first the first 16 of the sequence if your language does not support arbitrary precision, array as many as you can. Alright, so it's pretty open. It says like, well, if you can, do the first 16, otherwise don't. So we start off with a list of 2. And then, well, we find a bunch of other ones. So let's first do 3 of them. So what we do is in which element is the least prime factor of 1 plus the product of all earlier elements. So the product of all elements is the product. And then we add 1. Do that. And then we get the what do you call it? Factor integer. Factor integer. So it gives prime and then the multiplicity basically. So we do this, we get all the primes and then we get the minimum. Which is the least prime factor. Okay, so now we do append to list that number. Let's say like new. And then let's show. Okay, what is the? That seems to be correct. Okay, how many did we have to do? 16. So I have to put 16 minus 1 here because we started 1. Oh, it went pretty fast. Okay, so can we use strategical compute the next 11 elements of the sequence? Let's do here the list itself and the length of the list in a column, so we can see while it is running, we can see what is happening. So now we have 17 elements. Ooh, this one is really big, as you see. 19 elements. So of course the heavy operator here is this factor integer. And yeah, because of so this product will always be even because there's 2 here, but because you add 1 it's always odd. So there's probably no easy factorization here in general. This is a very strange sequence. Is this in the OEIS? Oh yeah, of course it is in the OEIS. So let's see what should come out of here. 887 is the next one. So I don't know how long this should take, but let's see what people have done here. So people have done the first 8 here. And this looks all of them. So in Fermat and in free basic. And it even takes forever to find the largest term, but goes there in the end. So it will work, but it might take forever to calculate. So in Julia they did the first 16. Also in Pari. But in Perl someone also did the next 11. So now I am here. So it's trying to find the factors. But yeah, if you do the product of all these numbers, you get some gigantic number, of course. Yeah, but this one seems a low number. This seems low numbers. This one seems a pretty high number. So I'll leave it running for a few more minutes while I see. Unless there is a function in Mathematica that can find the lowest factor in a faster manner. Of course, I can do it manually by just iterating the primes up to some point. then this one would be found very quickly, right? If it is, so this 887 has been found. Okay, let's see if it finds 71. So I don't know how the algorithm works, of course, because in principle we only need the lowest one. Yeah, but to find this one, that is quite a big number. But what you could do, for example, is first do this approach. But if it takes longer than, I don't know, 5 seconds, 10 seconds, try to just find them by brute forcing some, but even this one, so this is 1.3 billion, that is a pretty big prime number. I don't know which prime number that is, but it's probably millions or millions of prime numbers, so that would take a while to find if you write it manually, let's say. But anyhow, this is a stretch goal, and well, our code will find it at some point, so how long it will take, I don't know. But let's add this code, and then so how do I want to code this? Let's put this in. And then, wait, this is 21, right? Yes. So of course I aborted it now. So let's copy this. So this dynamic is not needed for the solution, of course. That was just for us to see where we are. And we can say the first 21 numbers of the sequence. Others may be found, but it will take a while. By adjusting the range of the do loop, it will take a while. Let's copy this. Okay, let's save this. Right. Great. Mersenne primes. Create code that will list, preferably calculate, all of the Mersenne primes until some limit is reached. The number of known Mersenne primes is 51, and the largest known Mersenne contains 24 million digits. So Mersenne primes are 2 to the power x minus 1, if I recall correctly. So these are actually implemented, I know, with some function called Mersenne prime exponent. So that will give them. I don't know how many people show, but we can also calculate them, of course. So select from range 100, or we can do I from 1 to infinity. Results is an empty list. If prime q 2 to the power I minus 1, then append to res. Res, what do I want to append? I think just I. if length res equals, let's say 10, then break. I'm not sure how fast. Okay, let's just see where it is now. I think it's also good to know I, but also the length of res. So I have some idea what it's doing. 15, 17, 18. So it's 4200. Okay, so how many did we have to do? Yeah, okay, so I think this is fine now. So we have, well, the lazy method, which is this one is done. Close this one. So we have the lazy method. I can say Mathematica has a built-in function to show the Mersenne primes, and this will immediately output just the numbers. Alternatively, we can calculate them so there you go. Copy this. And again, I'll remove the dynamic, which is nice, but not needed for this. So this will first show 20. I think that is respectable, let's say. And well, the others just take a lot of time to calculate. So let's see. Alright, well that's a bit long, but well, that's fine. Boom, another one done. Do I want to call, let's save it. Mersenne primes. It's a bit silly, this one. Alright, the n-body problem is an inherent feature of a physical description of a mechanical system of n interacting objects. The system described by Newton's laws, blah, which continues combined force from other bodies. Exact formulation of first mechanical problem is given initial coordinates and velocity at t0 to find the coordinates velocity at t0 with actually more than given relative value. As well known from physical background, only the choice element in this two can be analytically solved. Write a simulation of three masses interacting under gravity and show their evolution over a number of time steps, at least 20. Well, also here again, there is an n-body simulation function, and I am pretty sure that it has an example here of basically with gravity. So this will go as 1 over r squared. Yeah, here, unitless inverse square law. Do we want to? I think no units are given, no positions are given, so I think we can do whatever we want. So this is the n-body simulation, and yeah, I think we should just show some plot and some coordinates. Oh, does this work? And body simulation data. Okay, can I query state of body B at some time t? Okay. So we want to show it at 20 time steps. Well, it's not really steps, but what we can do is you subdivide. So we do from 0 to 5 seconds, and this, and then what do we want to show? All the positions and all the things. Do we want to do that in some nice format, let's say? And do we want to do it in 2D or 3D? Why then 3 mouses? So people do it here in 3D. I mean, it's kind of the same. So we can take all the bodies at that time, and then let's see how does this work again, this function, this object. So bodies, properties, time. Bodies, properties. So I guess this is a string. Yeah. This only simulated to 5 seconds. Here we go. So these are all the positions. Velocities. I guess that is velocity. Can I do a big grid? I think that is fine. I mean, I could do this in a column format. It will probably output very nasty. And then here, time, and boom. Well, let's do this. I think that is perfect, actually. I mean, it's by far the smallest code, probably of the Rosetta entries. So, okay, and body problem. Oh, no, let's save this one. Rosetta. Do I also want to have... I can also include this piece of code, such that people also see the graphical representation. Of course, I cannot include that into the... cannot upload images there, unfortunately. But I will say that the code outputs a graphical object. No. Yes. Copy this. Copy, paste. Now the question is, does this copy nicely into plain text? Yeah, it actually does. Outputs and graphics object showing the trajectories of the Save page. Just check. That's a bit messy, but it's fine. Alright, given a list of words, use the words from this file. Take the letters at odd indices letters from each word. If the result is present in the list, then display the result. The length of the odd word should be bigger than 4. Let's call it dictionary. $25,000, okay. Odd words, okay. Rosetta, odd words. So if I see this file, it probably doesn't make any sense, but well, what is this? Related tasks. Take the letters at odd indices. So odd is a bit weird defined because does it mean starting at to count at 0 or at 1? So Mathematica starts with indices 1, so I guess I will do that. Yeah, but let's make a function odd word q, which inputs a string. Well, inputs the parameters are a string input, the arguments. So I think there's a string take. Yeah, so the length of the odd word should be bigger than 4. So that means the word should be at least 7 long. Like if string length s bigger than 7, then do this. Otherwise, false. From beginning to end in steps of 2. And now, is there a member queue? Basically, what do we know? Member queue, member queue in the list. So dict commanders. I have this module. Well, this module is not really needed strictly in this case, but. So select from date. I have no idea how fast this will be, to be honest. Maybe it's also a good thing to show the original word. Huh? No, so this is fine. Yes. Let's make a function odd letters as string. Then what we can do is boom, comma. Of course I have to calculate it twice now, but it's not too bad. Alto. Is alto a word? Okay, but what if it is starting from 2? Okay. Barbarian. Do I have that here? Barbarian. Wait. equal to 7 as well. Abra. So I guess we want to do this definition. Let's use this new functionality. Divide. Here we go. Q, dig, comma, barbarian. Up. Okay. So bigger than 4. So this really has to be 9. Yes. Okay, here we go. I think. Yeah, okay. Here we go. We added nim. So this one can go. Let's first copy this header. And then let's copy this solution here. And the results will be this thing. Alright, let's save it. Okay, that's another one done. Your edit includes, yeah, okay, taxis. There's no taxis. Traffic lights. Crosswalk, this is very annoying. Traffic lights. I don't like machine being someone that helps the machine learning better. Click verify once there are none left. I don't see any bicycles on here. There's a bicycle. Oh my god, this is getting ridiculously annoying. Thank you. Alright, very good. Let's do another one. Own digits power sum. For the purpose of this task, an own digits power sum is a decimal integer which is n digits long, okay, and is equal to the sum of its individual digits raised to the power n. Example, the 3-digit number 153 is an own digits power sum because 1 cube plus 5 cubes plus 3 cubes equals 153. Find the show here all own power sums for n equals 3 and n equals 8. Optionally, do the same for n equals 9, which may take a while for interpreted languages. Alright, own digits power sum q n. So let's get the digits, so we can get that with integer digits. And then the length we can also get. Let's put those as local variables. So now we want to do digs to the power len, and then total, and then compare to n. That's really everything. So now let's do this for some range. this way or the other way? List and the criterion, yeah, here we go. Ah, but n should be bigger than 3, so I should start at 100. Alright. 370, 371. Okay, so 9 digits long, that is actually pretty big. Well, let's see how long 100,000 takes. That's not too bad. 1, 2, 3, 4, 5. 5 seconds, but we have 8, so that's 100 million. So this will take 19. Maybe we can compile this just to compile. And being an integer, let's see, what is the syntax again? Yeah, okay. Compact function. One, 2, 3, 4. 4 seconds, or can I also do compilation target C? Here we go. This will compile it in C, it might be faster. Okay, now I don't know which bit is what. Absolute timing for 10 million. 3.6 seconds. That is not too bad because we need 8 digits. Is there also some listable property or something? Parallel controls for compiled function. I don't use compiled enough to know runtime attributes. What does that mean? Maybe. Well, I guess this is fine. So what we can do? Yeah, let's kill this bit. Actually, also don't need this. And then the compilation is so fast that it is pretty much fine to do it like this. Probably this should take a minute or so, but meanwhile we can already put the code here. Let's first copy the header. Yeah, I don't have any idea when this will finish, how long it will take, because, well, the longer, okay, actually it finished. So it's 40 seconds, basically. So from the code here, I will remove the timing, because that's not really needed. And that is pretty good. What was the stretch goal? Was it 9 or was it 10? Yeah, do I want to do 9? So this, yeah, so this person also does 9. It'll take 10 times as long, so 10 times 37 seconds, yeah, it's 10 minutes or so, 5 to 10 minutes. I don't want to wait that long, I think it's fine. So what was it called? Rosetta, own, digits, power, sum. Here we go. An overloaded OR can be used on more than one data type or represent a different action depending on the context. For example, if your language lets you use plus for adding numbers and concatenating strings, then one would say that the plus operator is overloaded. Tasks demonstrate an overloaded operator in your language by showing the different types of data they can and cannot operate on, and the result. So, well, let's redefine how objects are, let's say, let's define a vector, let's say 1, 3. Well, a b, let's say a b, vec c d, vec a plus c, b plus d. I think I can do this. No, but I can do this if I, no, what was it again? This thing, I think. So if I now have one, well, let's say 4,7 plus, I don't know, 9,3. So the reason why you have to use the upset delayed, because then this definition is associated with vec rather than with plus, if I recall correctly. Assigns right-hand side to be delayed values of left-hand side and associates the assignment with the symbol that occur at level 1 in the left-hand side. So I guess maybe if I do this, sorry, small v. Yeah, so now this definition is assigned to vec and not to plus. So I think this is what they want to show, so just to overload the plus symbol in this case. So I'll just show that we can add vectors together. Of course, this is already built in, but you know, these objects can be anything. Define a custom vector object and define how plus works on these objects. Yeah. Oh no, not again. I really hate this when especially this stupid thing that it fades very slowly for some reason. Cars. I don't know why it is so slow. I have no idea, but they hate the Google engineer who made this. Maybe I solved too many Rosetta codes today. I think I did enough for today, so we can have a look. I will leave this for next time. We can go to Mathematica to see how many we solved now. 1141. So that's a pretty good number. As you see, many entries. And but still, there are many remaining as well, and also people continuously add them. Anyhow, this is it for this time. See you all later.